In our previous videos, here we are going to talk about continuity of multivariable functions. So in our case, we will restrict our attentions to functions in two variables like f of xy, although most of the discussions that we will talk about during this video will go through for functions in m variables, but as I said, for our purpose, we will restrict our attention to functions in two variables. To this end, let us take a subset D of R2 and a function f from D to R, a real valued function on D, and suppose that x0, y0 is a point in D. We say that f is continuous at the point x0, y0 that we have chosen here if the following is true. For every sequence xn, yn that converges to x0, y0, the real sequence f of xn, yn must converge to f of x0, y0. So I must emphasize that this sequence, the convergence of this sequence is really a convergence of a sequence of real numbers, whereas this is the convergence which is mentioned here is a convergence of sequence of two tuples. So this should hold for every sequence x and yn that converges to x0, y0. So we will see examples of this in just a moment, but let me first finish the definitions. So a function f that I have mentioned above is said to be continuous on D if it is continuous at every point of D, and f is said to be discontinuous if there exists one point, if we can find one point x0, y0 in D such that f is not continuous at x0, y0. So let me just try to illustrate when is a function not continuous. So when is a function not continuous? So this is purely a logical statement. So let us once and for all clear the air about this kind of things. So in order for a function to be continuous at the point x0, y0, as I have said, I need for every sequence x and yn that converges to x0, y0, we must have this convergence of real sequences. But what is the negation of that sentence? That means that there exists a sequence x and yn that converges to x0, y0, but f of x and yn does not converge to f of x0, y0. So in order to show that a function is not continuous at this point x0, y0, we must produce one sequence x and yn that converges to x0, y0, but f of x and yn that does not converge to f of x0, y0. So let us go ahead. So some properties of continuous functions which really follow from properties of convergence of sequences. So suppose we are in the case as we have mentioned before. So if you take D to be a subset of R2 and x0, y0 a point in D. So suppose that f and g are two continuous functions, or f and g are continuous at a given point x0, y0, then we can prove that the sum of these two functions is continuous at x0, y0. You can also show very easily that the difference of these two functions f minus g is also continuous at x0, y0. You can show that product of two continuous functions, product of two functions f and g which are continuous at x0, y0 is continuous at x0, y0. Moreover, if we have the condition that g of x0, y0 is not equal to 0, then the quotient of those two functions f by g is also continuous at x0, y0. So I'm inclined to skip the proof because this is so easy, but just let me give an example so that you can prove the rest. But I will leave, I will show that f plus g is continuous, but I will leave this too, and also that f minus g is continuous as an exercise, but this will give you some idea of how to do it. So suppose that x and yn converges to x0, y0 by continuity of f. we know that x and y and f of x and y n converges to f of x0 y0, and by continuity of g we know that g of x and y n converges to g of x0 y0. Now we know that if you have two real sequences, an converging to a, bn converging to b, then an plus bn must converge to a plus b. You just apply this formula over here to say that f of xn plus yn plus g of xn plus yn, g of x and yn converges to f of x0 y0 plus g of x0 y0. So now whenever you are given this kind of properties where sum and product of two continuous functions are continuous, so then the first example that should come to your mind is of a polynomial. So here we talk about what is a bivariate polynomial, and we say that bivariate polynomials are continuous functions. So bivariate polynomials are formally defined as follows. So it is summation of aij is a real number, and x to the power I, y to the power j, I and j, these things will be non-negative, and there should be only finitely many summands, and this condition I plus j less than or equal to k ensures that there are only finitely many summands. So here we fix a non-negative integer and we write down this expression. For example, for a concrete example, let us look at this polynomial. So f of xy is, let's say, x cubed plus 3x squared y plus 3xy plus 3xy squared plus 2y plus 3y squared. So I know that I plus j must be less than or equal to k. Here the value of k that I have just chosen is equal to 3. You can see that all the summands that I have taken here, if you consider I plus j, the degree of x and degree of y, if you add them, it is less than or equal to 3. So this is a polynomial, bivariate polynomial in x and y. So in order to show that this is continuous, note that we only need two things. The first thing is that I must have if xy equal to x is continuous, if xy equal to y, that is continuous. So if we have, so let me call this g for avoiding any confusion. So g of xy is equal to y is continuous. It is very easy to show that these two functions are continuous. So for example, what you can do here to show that this function is continuous, you have to start with any sequence x and y n that converges to a point that you want to check continuity of f at. So I have taken this point to be x0 y0. So what does it mean to say that xn yn converges to x0 y0? So it simply means that xn converges to x0 and yn converges to y0. But you see but this is exactly equal to f of x and yn by definition, and this is exactly equal to f of x0 y0. And similarly, if we check carefully, so this is exactly yn is exactly g of xn yn, and this guy is exactly equal to g of x0 y0. So this proves the continuity of the functions if xy equal to x and gxy equal to y. But once you have that, you can take, so we can say that whatever I choose, x to the power I is continuous, Now whatever value of j I choose, y to the power j is continuous. Now if x to the power I is continuous, y to the power j is continuous, then the product of them is again continuous. X to the power I, y to the power j is continuous. Then there is one more thing that is also very easy to show, is that if you take another function h of xy, which is a constant c, that is continuous. This is also very easy to prove, and once you have that, so we have that this function is continuous, a constant is continuous, so whatever aij you give me, this product is going to be continuous. And So you can add two of this kind of terms, and then you get continuity of the sum of two of these terms. And if you do this inductively, you can see that if you have finitely many summands under this summation like here, then this sum is also continuous. So let me work with this example here that I have just written down to make things clear for you. So using the properties that fxy equal to x is continuous, I can see that x cube is continuous. I can also see that x square is continuous, y is continuous. So that means that this term x square y is continuous, and since h of xy is equal to 3 is continuous, I can see that this whole thing is continuous. Now I can say that this is a continuous function, this is a continuous function, so sum of these two functions is also continuous. So similarly I can incorporate the next thing. I can incorporate the next thing also here, so I can also prove that this is continuous. Now if this is continuous and this is continuous, then this is continuous, so on and so forth. So it is very easy to show that bivariate polynomials are continuous functions. Next, we have to make use of the last part that we have just seen. So using this, we can prove that a bivariate rational function is continuous at the points where the denominator does not vanish. So first of all, what is a rational function, a bivariate rational function? So fxy is called a bivariate rational function if it can be written as pxy by qxy, where pxy and qxy are bivariate polynomials by variate polynomials. So if we look at a point x0 y0 such that g of x0 y0, also not g here, it is q, such that q of x0 y0 is not equal to 0, so then at that point pxy by qxy is continuous because of the last property that we have seen. So we have seen that polynomials are continuous, so pxy is continuous, qxy is continuous, and at this point qx0 y0 is not equal to 0, so this function is continuous at the point x0 y0. Now let us go ahead and do some more things. So now we are going to say that composition of two continuous functions is continuous. This is not proved in the all possible generality that you can talk about, but here is our statement for the purpose of this course. So suppose you have R2, so you have a subset D of R2. Now you have a subset of the real line, so this is R and this is RE, and suppose that f is a function from D to R. So f is a function from D to R such that D is mapped inside this subset. So do not mistake E to be an interval. It need not be an interval, but I hope you understand that E is just a subset of R. So suppose that f is a function from D to R such that f of D is contained inside E. Also suppose that I have another function g from E to R. So then I can talk about the function g composite f from D to R. How is it defined? So you pick up a point x0 y0, so g composed f x0 y0 is nothing but g of, so what you can do is that you can first compute what is f of x0 y0, so this falls in E, so this falls in this region, and you know that g is a function from E to R, so you can then compute the value of g at this point f of x0 y0. So this is how compositions of functions are defined. I'm sure that you have seen this kind of examples before. So the hypothesis says that if f is continuous at x0, y0, a point that you have chosen randomly over here, so a point, suppose I have chosen a point randomly over here, x0, y0, so then this point is mapped to somewhere here, and this point is called f of x0, y0, and then the image, when the image inside R, this is g of f of x0, y0. So it says that if f is continuous at this point and g is continuous at this point, then g composed f is continuous at this point. So this is very easy to prove. This is very easy to prove. How do we prove it? So you take a sequence x and yn which converges to x0, y0. By continuity of f, we see that f of x and yn converges to f of x0, y0. So since f is continuous. Now we apply g, and since g is a continuous function from e to r, so we apply the sequential criteria for a real valued function of single variable to be continuous at a point. So g is a function from e to r, g is continuous. So g of f of xn converges to g of f of x0, y0. So this satisfies the sequential criteria of convergence of a multivariable function, and consequently g composite f is continuous. Now this happens because g is continuous. This happens because g is continuous. Let us look at a small example. So suppose that pxy is a polynomial, and we have seen that this polynomial is always a continuous function. So then e to the power pxy is continuous. So for that I will make a diagram. So there is a map from R2 to R which is given by p of xy, and there is a map from R to R which is given by e to the power z. So this function, we have seen in calculus 1 that this is continuous, and you have just proved that a bivariate polynomial is continuous. And but by what we have said just above, the composition is continuous. And what is the composition of this? So suppose I take xy in R2. So then when I apply p of xy, so then the image is p of xy, and so then this belongs to R. And then when we apply this map, then we get e to the power pxy. So as I have said, that the composition of two functions is continuous, and consequently e to the power pxy is also a continuous function. Now in analysis or calculus, most of the definitions that you will come across will have a epsilon-delta definition that will go through. So what is the epsilon-delta definition of continuity in this case? So suppose that we have all the conditions that was mentioned before. D is a subset of R2, f is a function from D to R, and I have fixed a point x0, y0 in D. So we say that f is continuous at x0, y0 if and only if the following epsilon-delta criteria is satisfied. So for every epsilon greater than 0, there exists a delta greater than 0, such that whenever xn yn minus x0 y0, the norm of this is less than delta, we have f of xy minus f of x0 y0, and modulus of that, it is less than epsilon. So you have to be a bit careful with this kind of notations. So here the distance between 2 points that I have mentioned is actually calculated inside R2. So whatever is going on here, this is happening inside R2. So we must use the norm here. Now f is a real valued function, so whatever is going on here, the difference between f of xy and f of x0 y0 is happening inside R. So here we have to use modulus of that. Now what do we actually mean when we say all this kind of things? So suppose that here is a two-dimensional region that we have D. It is contained inside R2, and suppose that I have R here. So suppose I have a map F from D to R as it is given here, and suppose I take a point, I choose a point x0, y0, and I want to test continuity of the function f at this point x0, y0. So this point will be mapped to some point here which we will call f of x0, y0. That is the definition of a function. Now, what is the epsilon delta criteria? Epsilon delta criteria says the following: you give me any epsilon which is bigger than 0. So you give me any epsilon which is bigger than 0, and then I will consider this interval. So what is this interval? This interval is f of x0, y0 minus epsilon and f of x0, y0 plus epsilon. So this is f of x0, y0 minus epsilon. This is f of x0, y0 plus epsilon. So you give me any epsilon, I will consider this interval, and then I can produce a delta such that if I take a disk of radius delta, then this disk, so let me use another color, then this disk gets mapped under F inside this region, So again, you have to give me a delta, you have to give me an epsilon. I will draw this open neighborhood of this point f of x0, y0, and corresponding to that value of epsilon, I will produce a delta greater than 0 such that every element in a open disk of radius delta around x0, y0 gets mapped inside this interval f of x0, y0 minus epsilon, f of x0, y0 plus epsilon. I hope this clarifies the epsilon delta definition of continuity. Now we are almost ready to finish off the video, but before we finish off, let us look at a couple of examples of continuity. So suppose I give you a function which is given by f of xy, which takes value xy divided by x square plus y square if xy is not equal to 0, 0. Note that this condition ensures that this term is not equal to 0. The denominator does not vanish at all at these points. But how do we define? So we simply say that f of xy is 0 at the point 0, 0. Then we have to check whether this function f of xy that we have just defined is continuous or not. Now the expression that we have here is an expression of a bivariate rational function. We have seen that bivariate rational functions are continuous at all points where denominator does not vanish. Here what is the denominator? X square plus y square, and if you take any point which is given by which is not equal to 0, 0, we can see that the denominator does not vanish. So if you give me any point which lies in this region, which is not the origin, this function is going to be continuous. The problem happens at the point 0, 0. So we have to check the continuity of f of xy at the point 0, 0. So let me take a sequence, and in this case a particular sequence 1 by n comma 1 by n, and we can see that this sequence converges to 0, 0. Now in this case, what do we have? What is f of x and y n? This is given by f of 1 by n comma 1 by n, and you can see that if this 1 by n comma 1 by n is not equal to 0, 0. So we have to use this definition, and if I plug in this information by replacing x by 1 by n and y by 1 by n, we will see that what we will get is equal to 1 by n square divided by 1 by n square plus 1 by n square. and you can see that this is a constant sequence. This is always equal to half, and consequently as n tends to infinity, this sequence goes to half. But then if the function was continuous, then f of x and y n should have converged to f of 0 0, which is equal to 0. Since half is not equal to 0, we say that this function is not continuous. Not continuous. So let us proceed. Let us take another example. Here what I have done is that I have just multiplied the previous function by x in the numerator. So I have taken f of xy to be equal to x square y divided by x square y square if xy is not equal to 0 0, and 0 if xy is equal to 0 0. Okay, so then by the same argument as above, if I take any point x0 y0 which is not equal to 0 0, this function is continuous. So no need to check, because this is a bivariate rational function, and in such a point the denominator does not vanish. So what happens if we consider the point x0 y0 to be equal to 0 0? So let us compute this difference or estimate this difference. Let's say, so f of xy minus f of 0 0. So we know that f of 0 0 is 0. So I have taken modulus of this. So this gives me modulus of x square y divided by modulus of x square plus y square. So the denominator is always non-negative, and so in that case I can just remove this modulus sign here, and what we do is that I write it as mod x times mod xy, but then this quantity is less than or equal to modulus of x by 2. How does it follow? So to prove this thing, all you need to show is that modulus of xy divided by x square plus y square should be less than or equal to half, which is same as saying that xy divided by x square plus y square must lie between minus half to half. Now this is very easy to check. The first thing is proved by saying, for example, x plus y whole square is always bigger than or equal to 0, and this is proved using the fact that x minus y whole square is always bigger than or equal to 0. This is very easy to prove. And modulus of x by 2 is less than or equal to modulus of x. Now you take any sequence x and y n that converges to 0 0, you can see that f of xn comma yn minus f of 0 0, by what we have proved here, if I call it inequality 1, so by 1 we see that this is less than or equal to modulus of xn. And then what do we need to check? We need to check that this guy must converge to this guy, and this is now a consequence of let's say sandwich theorem. So this guy is always bigger than or equal to 0. So this is a constant sequence 0. This converges to 0. Modulus of xn, this converges to 0 by definition. Xn yn converges to 0. 0 0 implies that xn converges to 0, yn converges to 0. So this also converges to 0. So this sequence that we have in the middle must converge to 0. So this proves that. So using the fact that modulus of an converges to 0 implies an converges to 0, we can see that f of xn comma yn converges to f of x0 y0. I got a couple of more examples. So what we have proved is that of course this map f is continuous. So this function is continuous. So a couple of more examples. So suppose I take f of xy to be this function, x square y divided by x to the power 4 plus y square, x to the power 4 x square y divided by x to the power 4 plus y square if xy is not equal to 0 0, and 0 if xy is equal to 0 0. Then is this function continuous? So we will again see that this function is not continuous. So how do we prove it? First of all, we do not need to really check check continuity at points x0, y0 where it is not equal to 0, 0. Why? Same reason, x to the power 4 plus y square is equal to 0 if and only if xy is equal to 0, 0. And this is a bivariate rational function. If this is not vanishing, if the denominator does not vanish, then it is continuous. So at all points other than origin, this function is continuous. What happens at origin is something to be investigated. So here I have taken x n y n to be a sequence 1 by n comma 1 by n square, which converges to 0, 0. You can see easily. And where does f of x and y n go? It goes to half, but half is not equal to 0, which is the value of f of 0, 0. So this proves that the function is not continuous. The function is not continuous. So I leave it to you as an exercise to check what happens if we instead take the sequence x and y n to be equal to 1 by n comma 1 by n. Okay, so the last example of this video is the following. Again, like I did in the previous example, I have just multiplied the numerator of the previous example by x. So again, everything goes through word to word that we do not need to check continuity at points x0, y0, which is not the origin. So everything that we need to investigate in order to check continuity of the function f is to check continuity of the function f at the point when x0, y0 is equal to 0, 0. So we can use the same method that we have employed to check our example 2, and the same thing happens. It turns out that f of xy minus f of 0, 0 modulus of that is less than or equal to modulus of x by 2, which is in turn less than or equal to modulus of x. So you can now choose a sequence x and y and just exactly how we have tackled the example 2. You can choose a sequence x and y and which converges to 0, 0, and you can apply exactly the same argument to show that f of x and y and converges to 0. So this is all about continuity for the time being. We will see more examples in your exercises.